Okay, welcome to this next video for Chem 161. Well, we'll continue looking at electronic configurations, speaking to the ground state of, in this case, some neutral atoms and ions, and looking at a shorthand notation called noble gas core electron configuration that helps us identify valence electrons. Okay, so let's start with trying to determine the ground state electronic configuration for a neutral atom that is the bromine atom. Okay, so here's a moment where you might pause the video, practice your skills from having watched the previous video, and look to use the periodic table to help you complete the correct order for the bromine electronic configuration, again in the ground state. Okay, so hopefully your eye went to the periodic table and you identified the bromine atom over here at spot 35. So we're going to have 35 protons in that atom, which means that we have 35 electrons to list in our electronic configuration. Okay, we recall that there is an S block, a P block, a bit of an exception here in that we call that spot the 1s2 option for helium, and then we have the D block and of course the F block down below. And we need to simply walk left to right like we do reading a book, going row to row, building towards bromine. Okay, so we start with 1s2 for the first row, 2s2 for taking us all the way to beryllium. We now introduce the 2p's by jumping across to the first row of the P block. 2p6 takes us all the way across to our neon atom. Still need to go further. We'll go to the third row, and now we have a 3s2 taking us to magnesium. Jump across to aluminum, and we have the 3p set. Room for 6 electrons there. 6 elements take us all the way to argon, the next noble gas found here in the series. And then we'll go down to potassium for a 4s2. We now have to list some of the D block because we've got all these transition metal elements to do. So as we transition from calcium to scandium, we see the 3D, note the 3, even though we are in the fourth row. And going all the way to 10 takes us to zinc. And as we move into the P block again, we go back to 4p. Notice that we don't have the same number there. We've already used 3p. So 4p. And we finally go 1, 2, 3, 4, 5 spots over. 4p5. You can check the total. Total of your exponent should be 35, as indicated by the atomic number of the neutral atom in question. And so we've got 10 up until here, another 10 there, and 15, so that would be the 35. So there's our correct answer for the bromine. Now, the next one I'd like you to try to think about, and again, you can look at doing the electronic configuration for an ion. So we'll look at doing this for bromide, which of course is Br minus. So try to do the electronic configuration for the ground state of this ion, repeating what we know from the neutral bromine, but of course respecting the idea that we have a charge here now. Resume the video when you're ready. Okay, so the trick here is to recognize that we have an imbalance between the number of protons and electrons here, so we have to have more electrons than protons to have a charge written up here in the subscript to the right of the element symbol. So we have to have one extra electron relative to the neutral bromine. So one extra electron means 36 electrons total, rather than the 35 that we see in the periodic table, which would speak to with 35 would speak to the neutral bromine, but we've got to go to the bromide, so we've got to create the ion. So a lot of it is going to look similar. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p6 this time to indicate that extra electron. Okay, so we can do electronic configurations not only for excited state atoms, excited state ions as well, and so you can refer to the previous video for that one. And here we've shown the bromide electronic configuration, reflecting that extra electron at the last spot. Okay. So as we'll see, we're going to be able to list valence electrons, which speak to the electrons in the outermost regions, or the highest energy spots in our energy level diagram. So often what we see here are the final orbitals populated with electrons that are at the highest energy levels. Okay, so we'll just rewind a little bit and remind ourselves of that. So often the higher energy orbitals that are occupied, depending on the atom, of course, would be the most reactive, and those are going to help us with bonding. Okay, so to help us identify that list, we're going to have a noble gas electronic configuration. Okay, as you can see here, in comparing bromine and bromide, a lot was similar, and everything that changed was towards the end, as we included an extra electron. And so what we do to help us show that there's core electrons that are quite unreactive, and that there are electrons at the higher energy levels that are reactive, is we use the nearest completed noble gas electronic configuration to help us for our shorthand. Okay, so the noble gas configuration we're going to use the previous, so the nearest most previous noble gas as a starting point. Okay, so looking at neutral bromine again, okay, so referring to the red script up above, we recall that we've got bromine at the 35th spot, and so we have to walk backwards to identify where we can identify a shorthand noble gas core that we can use. So we're going to use the argon. It's the nearest most complete electronic configuration. Recall that that was 18 electrons. So the 18 electrons took us all the way, there's 10 to here. And so we're going to take all of this and put it in our shorthand simply as argon with square brackets. Okay, so when we see that, that indicates 1s2, 2s2, 2p6, 3s2, 3p6. Okay, perfect. So then now we can continue the exercise. So we've started at argon. We go to the fourth row, so we know that we have to list 4s2, 3d10, and 4p5 if we're doing the neutral bromine. Okay, so that's how we use a noble gas core as a starting point to help us with shorthand for this same configuration information. Okay, so note when one uses helium that the helium shorthand would only indicate 1s2. So right there, that 1s2 is the electronic configuration for helium. Perhaps a little bit out of alignment out of all the others, which end with a filled p orbital. The helium has a duet instead, with only room for 2 electrons. Okay, so we mentioned that we can use this to help us with the identifying the valence electrons, which are the most reactive and would be used for bonding when we consider making molecules and other reactive transformations. So we'll remind ourselves here of the neutral bromine. Okay, so we saw that we were going to use argon as a starting point and then jump right away to the 4s2, 3d10, and finally ending at 4p5. And so to help us identify the valence electrons, we want to identify all the electrons at the highest principal quantum number. Recall this was the first one, this was n. And add n minus 1 d for transition metal. So if the element in question is a transition metal, we are allowed to add n minus 1 d orbitals to the valence listing. If the element is a lanthanide or an actinide located in the skinny part at the bottom of the periodic table, we are allowed to add n minus 2 for the valence electrons. Okay, so bromine is not a transition metal. So to list the valence electrons for the bromine atom, we can see we have to identify the highest principal quantum number in our list from our shorthand notation. So I see 4s here, and I also see a 3 on the 3D. I'm not allowed to include n minus 1. 4 minus 1 would be 3. I'm not allowed to include n minus 1d because bromine is not a transition metal. So the valence electrons are 4s2, 4p5. Total of 7 electrons, which speaks to the reactivity of bromine. It is very close to completing a noble gas core configuration by acquiring an extra electron, which speaks to how bromide is the most common ion to form because we want to complete this octet, as you may have learned in other courses, get to 8 electrons in this case. Okay, so here are a couple of examples. Let's see if we can do some others. So here's sulfur. The full notation is shown here. The shorthand is here. So see if you can identify, again, pause the video as needed, the valence electrons from either configuration. Yeah, so hopefully you flipped back and you saw that sulfur is not a transition metal. So we're not going to apply an n-1 kind of formula to help us include d orbitals in the valence listing. So we're simply going to identify the highest numbers. So 3p, 3s are the highest numbers in the configuration. We're not going to include any d's. They aren't even in here. So the valence electrons are here. Okay. Next one, strontium. See if you can do strontium. And here's only the shorthand notation. And again, list the valence electrons and resume the video when you've had a chance to do so. Yeah, so this one's a little bit easier. We've only got one orbital listed that's got 2 electrons in it, a 5s spherical orbital. Fifth row element, 2 electrons in it. This is neutral strontium, so we must be in the second column, and our valence electrons are therefore right there. Okay, how about gallium? Here's gallium's shorthand notation. Again, try to apply the rules above in the red box to help us identify the valence electrons, and resume the video when you're ready. Okay, hopefully you saw again that gallium is not a transition metal. And so we've got 4s2, 4p as the highest n values. So we're going to list those as our valence electrons for gallium. Vanadium. So here's the shorthand notation for vanadium, starting with argon as a start point, 4s2, 3d3. And again, use the rules above to help you identify the valence electrons from this electronic configuration in the shorthand form. Good, so you can see here, hopefully, that vanadium is in the transition metals. So we are going to use both the 4s, the highest principal quantum number orbital, 4, and we are allowed to use 4 minus 1, 3 this time because vanadium is a transition metal. So we're going to use those as well. Okay, so again, this exercise of identifying the valence electrons is very important. These tend to be the electrons that are highest in energy. On our energy level diagram for these orbitals, you see them listed towards the end of the electronic configuration list. And we start to see patterns when we look at the periodic table. So this is an abbreviated periodic table. Note the dotted purple line where we've excluded the transition metals to focus on some trends. In the first row, the valence electrons are represented by 1s1, and then we have helium here that has a complete duet. And these would be unreactive unless we took helium to some extreme conditions. When we look at the second row, we've got 1s2, 2s2. That's a second column periodic table. We jump the transition metal block. There is no transition metals in the second row, but we jump across now to continue for the main group elements here over into column 3 in that regard. And we start seeing some p listings in the valence electron count. We build ultimately towards a complete outer shell with 8 electrons this time, which speaks to a complete octet and very much a stable electronic configuration situation. This pattern of having octets all the way down the noble gas configuration is what makes the noble gases so stable and so unreactive. Patterns continue in the rows, in the valence electron configuration, 3s1, 3s2, jump across, 3s2, 3p1, 3p2, 3p3, 3p4, 3p5, and ultimately the argon octet. Okay, so this is reflecting again the valence electrons found for the main group elements, excluding those that would be in the transition metal area, but you have on the previous slide the rules for that shown here. Okay, we'll just end briefly commenting on a couple of exceptions. So it's interesting that in these transition metals that are chromium and copper, that you see this listing for their valence electrons breaking the trend, in that you would predict that chromium's valence electrons would otherwise be 3d5 or 3d4, 4s2. Notice the 4s2 in the neighboring elements to the left at lower atom number. So it's known that there's additional stability by half filling the d orbitals. So this d orbital can accommodate, these d orbitals can accommodate up to 10 electrons. Recall that that 3d level had 5 options for m sub l, 5 different orientations for the d orbitals. And if we can half fill this, 1, 2, 3, 4 was the situation as listed. If we can find a way to half fill it with these unpaired electrons, this is going to be more stable. Okay, so the 3Ds are shown here. In the case just shown, the 4s is shown there at a close energy level to that, and I'll show here that same 4s for the exception that we have listed below. And so this is going to be 3d5 as we see in our diagram here, and 4s1. So what's happened is we have borrowed 1 electron from the 4s orbitals that are very close in energy and populated that last spot to half fill the d orbitals. There's additional stability imparted onto the atom when it can do this, and that's why the electron configuration at chromium is an exception. We see the same thing for copper. So we're going to deviate from the 4s2 situation and fully fill the d orbitals to stabilize the atom just a little bit better. So again, the 4s is compromised. We drop down 4s1 to jump from 3d8 to 3d10 instead of listing a 3d9 as we would otherwise predict for copper. So for copper, the valence electron configuration is not 3d9 4s2, but rather we are going to borrow that electron from the 4s and fill the 3d orbital. So this will be a 1, and then we're going to go filled. So there's additional stability imparted by half filling the d orbitals as well as filling the d orbitals here. And that's how we explain those two exceptions. And we see something kind of similar here with palladium even, where it fully empties its 5s electrons to go to that fully filled d orbitals. Recall that in our energy level diagram for all these orbitals, as we go higher and higher in energy, the orbitals are getting closer and closer together. And so the idea of moving electrons from one high ns configuration to the n-1 d orbitals is very easy because the energy gap between the two is so small. And those are some